Hello. Welcome back to the channel, and now I think, well, we'll see, but this might be one of the last streams on the BSP. There was really just meant to be a quick one, but turned out to take a little bit to actually get more intuition about what BSP actually is. I mean, I might do a video on it, I'm not sure, but it is kind of fun going through and learning different concepts that are used in, like, you know, game development. And so I might actually continue doing something similar, except like maybe choosing something different each time, and just go and learn about it, and, you know, continue from there. So I think that could be pretty cool. But let's continue here. So I think that last time we went through the kind of the theory behind it a little bit more and got some more understanding. Well, at least I got, you know, I've been struggling with this one. Like, the BSP algorithm was it sounded good at first, and then you go but then you go into the details, and that's when, you know, I usually get lost a little bit. But then I came back around to kind of go back to the theory a little bit to understand, okay, well, now I'm kind of broken down the problem a little bit and understand how the actual partitioning is taking place and what kind of properties the nodes have and all that, and also how you can use it as well, because that was really confusing to me at first. Like, how would I actually use the BSP in order to actually get something out of it? But yeah, so now we got some more intuition, and I believe we left off last time implementing these front and back nodes. Now they can be empty or solid depending on different things. So I believe all the front nodes we set as empty, because that's kind of how the walls kind of work in this map that we have, and all the back are solid, the leaves, that is. If it's a branch node, then it doesn't have that information, basically. So a node can either be a branch, which means it has two children, front and back children, or it can be empty, which means it's like a void space that you can move around in, or it's solid, which means it's a solid space that you cannot move around in, which means that you should, like, collide with it. Oh yeah, so also we got to I can show you here. We got to the point where we solved some kind of weird crash last time, which I don't remember now what the cause was. Something to do with initializing the BSP tree. But what we did do was we tried to create the algorithm for running a ray and intersecting. So if I try to shoot here and I click the button, it should, like, get a red dot. I'm pointing at the screen with my finger. It should show a red dot here, but we can see that it's actually down here. If I turn my camera downwards, you can see it's down there. If I move over here and click, now it's down there. So it's like and the ray is always going, like, forward as well. So so it's just a matter of moving this dot. I'm not sure why it's all the way down there. Well, maybe there's a mismatch on the coordinates. Hello, Polaris7, or Polaris, welcome. Have a nice day yourself. Thank you very much. Hope you're having a good day. So let's continue. So I mean, that tells me that basically the intersection part does work. I mean, we basically copied an algorithm that already existed, but that is, you know, kind of how you learn these things, unless you're making up your own algorithms. which usually, for me at least, turns to some kind of unoptimized way of doing things, but it's a nice exercise anyway. But let's see where this is happening. So here we can see that the start position Y is taken here to be the Y axis, and that is like what is, you know, up or down. So that should be good, I would say. Depending on what we actually put in here, I think we just put the camera, yeah, the camera position. So that is strange that it goes like all the way down there. So we get the, and here's the cube definition that we get. So why would it be all the way down there though? Yeah, because it should have the same position as the camera to start with, and then the actual point that we return is using the same. Wait, no. Oh, wait. I'm taking, okay. It should be start. I was taking this one, which is a 2D, which throws away the Y. Okay. There we go. That was the issue. I just took the wrong Y thing there. Oh, wait. But now it's just at the start. Okay, so there's actually a problem, as we can see. Strange though, because it looked correct before, or maybe it wasn't ever correct actually. Okay, so this is not entirely correct. I mean, it might be the solidness of this, like, sections, that is the issue. Actually, you know what? No, yeah, if it's solid, we return the start position. But that means that should be correct, yeah. Yeah, so for this function, the idea was that it's kind of hard to explain now without a diagram, but basically the map is divided into nodes. And if the node is a leaf, the node is it kind of represents a rectangle on the map. So, and the rectangle can either be empty, which means it's, you know, it's like void space. It's like an empty room. It doesn't contain anything. So it's like, yeah, there's no collision basically. Or it can be solid, which means it's a solid block of space basically. So that means that we are colliding, and we just return any point here is colliding, but we just choose to return the start position. And so that is that. Is there something wrong over here? Because I'm pretty sure that the path we're taking is down here. Okay, and then but if it's not a leaf, we're down here. So now we have a node that is a branch, and that means the node it's a branch. It has a front and back node, but then it also has a plane. It splits the map, the whole space, in two parts in a binary way. So it has two children, front and back, and the plane is kind of the way that the whole map is split. So since this is a 2D, we're only working with 2D lines instead of 3D planes. But yeah, the principle is the same. It's splitting the map in two, and then we're checking, okay, how is our ray that we're trying to look with, how is the ray, what is the ray's relationship to this line or to this split object? So we're doing some calculations, and then we're checking, okay, well, if both, this means that if both start and end are at the front of the splitter, that means we only need to look at the front node. If both points are behind the splitter, we only need to look at the back. But otherwise, we're doing this we're splitting the ray up into where the first we're checking like we're calculating a midpoint, which is the where the ray intersects with the splitter, and then we're taking the start position of the ray up until that point, and that is either on the front or back side depending on the splitter here. Maybe there's something wrong with this calculation actually. I'm just gonna do this just to make sure it's the same, because these two sides needs to be different depending on the same coordinate. Okay. Okay, what if we move closer? Because the ray is like, it's not 100%. Okay. All right. So maybe this is the issue. Like it should be the other way around here. Like this should be the back and this should be the front or something like that. I was pretty sure that if these are positive, then the result is like in front of the line and this is like behind. I was pretty sure that was the case, but maybe not. Maybe I was wrong. Okay, maybe we don't even take that path because we are doing that. So actually, if T1 is in front, we should start in which the stat side is on the front side, yeah. So what if this is wrong here? Let's flip this around. And then I think these should also flip in that case. No? I don't think that worked well. Okay, well, it probably doesn't work too much. Now I get this one. Okay, so now it kind of depends. That's kind of weird. Okay. Yeah, that doesn't look correct. This is at least consistent. It always starts. It might be the solidness. Oh, look at this. Okay, we kind of have the same properties here. It feels like there's some dimension that is wrong here. If I move on this side, it like moves closer. Yeah, definitely. Okay. Is it the calculation of the midpoint, perhaps? Good morning, HP. What's up? We'll probably do... Yeah, I forgot to mention. We'll probably do quite a quick stream today. Same as yesterday. It depends on when my family gets home, basically. All right. I mean, yeah, this could be the issue. The midpoint is wrongly calculated. It's also weird that depending on which side we were standing on, the position was different. So let's look at our diagram here again. So this would be solid because it's behind, it's a leaf that's on the back, which is initialized as solid to start with. And we can also see like this point here is the start point of the ray. So it would be in front of this one. The normal points in this direction, but I think that we have to look at the normal actually starts from the origin and points to the right. So maybe that's an issue as well. Maybe the normals need to be different. Because we're taking the normal, the dot product of the normal to the start position. Maybe the normal needs to be like right now it's like relative. Hello, Buffer. What's up? What's up? BIOS boot sector. So, I mean, yeah, I think that we need to add... Whoops, you're not seeing this. I think we need to add the splitter. So basically, if we add... No. Wait. Like, I don't really understand this equation here. It's like we're taking the normal, let's say this one, so I'm gonna make a mini universe down here. This is the origin. Okay, the normal would just be like this. It would be like a copy of this here. Whoops. Okay, but then the player position is like over here, so it's like slightly down to the left, so it's like over here somewhere. So it's not really the same, you know. We have to shift this arrow to match the position. Like we have to, I think, wait. Yeah, it has to. Also, is the normal like situated at the center here? No, it doesn't matter on the y-axis. The only thing that matters is this axis, I think. So it has to be moved. You know, over here. And now it should be correct, because now the dot product because I think this is what's happening now. We're taking the dot product of this onto this. Which is basically this here. Okay. So the dot product of this onto this is like... It should be negative. You're watching me on TV, yeah? Cool. Hey, I'm on TV. I mean, okay. I think that's negative because they're pointing in different... They're pointing in different directions. But it doesn't tell us if this is on this side or this side. That's what we want to know. So I think we need to move the normal. The normal needs to like move first. It's like we need... But then they take... Okay, so first they take this and then they take the distance of this plane. They take the whole distance here and take minus at the end as well, which makes it even more negative. Which I don't understand that calculation. Like I would take like this arrow, make it relative to this plane. I guess we'll move it to the center. We have a point at the center here. So first you have a vector that goes from here to the center. Whoops. Hang on. From the center to like the center of this one, which is basically over here. So this vector here. And then you add this normal. So that you go back maybe like over here. So this would be the actual comparison that we do. Wait. No, we need to... God damn it. I'm trying to intuitively understand this. It's like you're taking... So the dot product of this on this is like you project a line from here to this line, except it's like it's perpendicular. So imagine this line continues for all eternity, like so. Okay, then you take this and you project it perpendicularly onto this line, so something like this, and that the length of this up to there is the dot product. Like the length from the origin to there. So then now we get a new line, a new vector, let's say, that goes up there. And this is the normal, or I mean, this is the dot product. The length of this arrow is the dot product. And because it's going in the opposite direction than the normal, or than this arrow here, that means that it should be negative. If it was going this way, it's positive. That's how I see the dot product intuitively. So it's a way that you can tell if a point is like, if two vectors are pointing in the same direction. One of the things you can do with it is like, are they pointing in the same direction? Then the number should be positive. Are they pointing in different directions? Well, okay, they're pointing in the same direction. You know, if you imagine a circle and you divide the circle in two, are they in the same semicircle? No, wait. No, that's not correct. Yeah. You have a circle like this, which is, you have a line that's perpendicular to this one, and here's the circle. Is this arrow inside this circle here? If it's not, then the number is negative. If it is, the number is positive. So that's how we can say that, okay, are we in front or are we behind a place? Try drawing an imaginary vector in the opposite direction of the blue vector. Okay. Then what? So now now this one should be inside the semicircle that we saw earlier. So it should be like, if you take the cross or the dot product, I mean, from this one onto the yellow one, it should be positive now. Yeah, but we're doing the opposite. We're taking the that's not what we're doing. Like in the calculation. Like this one, this is the normal of this wall here, or this line. Wait, if you project the yellow onto the normal, yes, it's negative because this is the actual direction. I should probably not have done like an arrow here. It just goes like this, and this is the midpoint. Yeah, so if you project over here, it's going to go negative. If this were pointing over here, it will be positive. And this one is like projecting over here somewhere, it's negative. If this was pointing over here, it would be projected like over here, and it would be positive. Yeah, but the problem is that we're kind of losing the information of about the positioning, I think, because or I'm misunderstanding something. This is kind of the origin on the big picture here. Like the origin is like over here. Wait, where did that? I had a layer here. Okay, so here's like the midpoint, and this is this vector like this. That's the starting point, and this guy is like this. Okay, so we're kind of it feels like we're losing information about the position here, because the normal is like it's like relative to this line here. So where should this be now pointing? It should really point it should really be like this, like we point to like the midpoint or something. I don't know. Or I'm misunderstanding. Like I don't understand how this maths works out. So we're taking the normal, because the normal is it's just a direction. That's the thing. It's a direction. Hello, said who? Welcome back. How's it going? Yeah, and then what they do is they take, so the algorithm looks like this. I'm not sure if the normal is the correct vector that we're using, but this gets projected like this, and so we get a negative, some kind of negative negative a here. I'm not sure how to draw that, but we get a negative distance, which is this distance over here. Okay, it's kind of hard to show. Okay, and then they take this distance and then we take like so let's see, this, and then negative b, which is the distance of this whole line here. This is b. So it's like, it's, I don't know, it feels like it's always gonna be negative if it's like a huge, if it's like a very long line. So I'm not sure if this is the correct thing. Oh, I'm sorry to hear that. Yeah, I hope it works out for you. Are you having, like, what kind of troubles is it? Or if you don't need to talk about it if you don't want, but yeah. So the distance, I was taking that as just the length of the splitter, but I mean it could also just be because that doesn't actually matter. Like, I don't know why we would need that in our calculation. It could be the distance to the origin, so it could be like the midpoint of the origin, maybe. No, because it's a scalar. I don't know. It could be the distance from the origin? Maybe? You're having issues redoing apps architect. Okay. I was thinking more like other types of issues. Okay. What app was that again? If you haven't said it. So let's look at this. Distance of the plane. Like, I don't know what that means. Do they show?
To its splitting plane and the indices of its children in the array. Leaf nodes are not stored directly, but are implied by a negative child index, -1 for empty.
Don't understand how dot product calculates distance? No, it's not a dot product distance. It's just a distance. Look at this. They have something called distance here. I'm just trying to figure out what that is. I don't like this is the calculation. And take the dot product of the normal of the plane, and then one of the points of the array that we're using here, start and end points. So we have two calculations, one for each point. And then we have the plane distance minus plane distance, but it's a scalar. I don't know what it signifies. So I'm trying to figure out. Oh, sorry. My bad. Yeah, here. So in this calculation here, yeah, sorry, I had the wrong screen up there. There's two calculations, so one for each point of the array that we're casting. So we have the start point and the end point. T1 is the calculation for, or P1 is the starting point, P2 is the end point. T1 is the calculation for the starting point, and T2 is the calculation for the end point. So what they're doing is they're taking the dot product of the normal of the plane against the point, to get, I don't really understand this calculation, and then they take minus the distance, but I don't know what this distance means. I thought it was like the length of this plane, but I'm not sure why this would be used in the calculation. Like, let's say the normal is pointing like, I don't know, is pointing over here like this way. Or is the normal not, is the normal like going with the, it could be going with the line. Yeah, I know what dot product is. I know what it is. I'm just trying to figure out how they are using, like I can see what they're using here. It's like deciphering a language here almost. Like I can see that they're using the dot product of something they call the normal of something. And then P1, which we know what P1 is. We don't really necessarily know what normal means in this case, or the plane distance. Because they can say that the normal is like, well, it's the direction of this line. I was suggesting it meant the perpendicular to the direction of the line. So it's rotated 90 degrees. That's what I was thinking. But maybe it's not. Maybe it's not rotated. It's just going up with the yeah, because normal usually means the perpendicular line, like it's going outwards from the thing. It doesn't go like with the direction. But maybe it is outwards, like I don't know. They're trying to calculate distance P1 from wall. I think they're trying to calculate if the distance doesn't matter. It's if it's in front of the wall or if it's behind the wall. That's what this calculation is about. It doesn't matter how far it is from the wall. The only thing that matters, well, this number might represent how far it is from the wall, but that's not what we're trying to compare later here. We're only interested if it's like positive or negative, which means is it in front or is it behind the wall? That's the only thing we're interested in here. Yes. I'm just trying to figure out this equation here because the normal is just a vector. To me, the normal is like a direction. It's just a direction. It's like a relative direction, and it's meant to be used in conjunction with the plane or whatever it's representing. Yeah, but the comparison, I understand this comparison. That's not the problem. The problem is this, the calculation. That's the thing I'm trying to figure out. What is the full form of T1 and T2? What do you mean? What do you mean by full form? And what's plane distance? That's the question I've been asking. That's the question I've been asking. That's what I said before. Like I asked, like, what does this mean? What does plane distance mean? What does that represent? And what exactly is normal in this case? So that's what I'm trying to figure out. So if we go back here,
were calculated during level development and are distributed with the game as part of the compiled map.
And maybe we'll get some answers.
The nodes are stored in an array, and each node contains a reference to its splitting plane and the indices of its children in the array. Leaf nodes are not stored directly, but are implied by a negative child index, -1 for empty and -2 for solid. The function to find the contents of a given point, SV whole points contents, navigates this tree.
But here distance is already calculated. It seems they're just using this
from node to node until a leaf is encountered. It is implemented as a simple loop, first checking the side of the plane that the point is on before moving on to the appropriate child.
The side? If type is less than 3, I think that means it is a leaf. Maybe? No? Wait. No, plane type. What the hell is plane type?
Simple loop, first checking the side of the plane that the point is on before moving on to the appropriate child.
P? Oh, maybe it looks like a dimension. And then minus the distance. So they stay the distance. Hello Cbit, what the hell is a BSP? that's what we're trying to figure out. No, but yeah, we've done a couple of streams on this now, learning from scratch basically what it is and what it's used for, and so basically it's kind of like it's like an optimization algorithm for rendering a 3D world. I mean, yeah, it was used in Doom and Quake, I guess most notably. But I believe it was used also like in Half-Life, if I don't remember incorrectly. You basically generated a BSP from the map data, and it would help you with things like optimizing, rendering, collision detection, and maybe even other things as well. Maybe even pathfinding. I'm not sure actually. I think plane distance represents distance from origin. Yeah, that's what I thought as well. It's like the kind of the mid coordinate maybe of the plane. The shortest distance from the origin. Perhaps. Hello Penguin, welcome back. The
function stops when a leaf is encountered. That is to say, when the node index becomes less than 0. Next, let's look at tracing a line through a level. This is done at many...
Okay, so how would that look in here? So we take the shortest distance is like this. So it would take this, which is a negative number, minus this, which is always positive. So it's like we get even more negative at that point. I don't understand this really. Unless the distance can be negative as well. No, it can't. It has to be positive. Because there's no like sense of dimension. It's just a distance. So it's like this distance here. This is B. And this doesn't actually make any sense. I'm working with, I like working with low pixels. Low pixel resolution stuff. But yeah, it's not really that great for mathematical stuff. No, this can't be correct. This cannot be correct. Because it's like what we want to do is we want to calculate the normal. Like I would, if I did this, I want to do, we have this arrow here. And then we have like this arrow here. So it's like, if we want to check if we're in front, we have this arrow here, or I mean, no, it should be this arrow here. No, that's not. Yeah. Or we make this arrow relative to the No. That's not correct. No, what we do is we take this arrow. So we take this. We get this arrow here. This is the arrow we want, I think. So it's like we go here and then down here. So we take this, the position of this plane, or the shortest distance from the plane, the position of this point here. So doop, and then we take, and then we subtract, or we take, no, we take this point and then we subtract this point. Wait. We basically want this arrow here. So it's like we're gonna get something like this, an arrow like this. Okay, and once we have that, we can now take the normal, because now we're relative to this wall, and we can now take the normal and take and now we only need the dot product. We just need the dot product now. So, and that gives us if we're in front or in back. That's what I was thinking. Right? Is this correct? So this vector represents the player position relative to, or not the player position, but well, in this case it is the player position as well, but it represents the relative position from the plane wall, or the plane here, this line, to the point over here. So that is this arrow here, and then the normal is this normal here, which is just the direction of which direction the wall is pointing in. And then we take the dot product of these two, and if that's positive, we're in front. If it's negative, we're in behind. And if we do the same thing for this one, we should get an arrow like this. So then we get this arrow, which should be negative, clearly here, against this arrow. And if let's say the wall was like, let's say we had a wall that goes like this, and then this is the normal, and then you want to take you have 2 points like this. So now we have an arrow like this, we have an arrow like that. We take the projection onto here, positive, projection onto here, negative, right? This should be correct. I just don't understand this calculation that they're doing. Maybe it's like a more optimized version, but I just don't understand it. I'm gonna change to make it like this. Because I don't know what they're working with. Like, the only thing we're missing now is like the midpoint of the so we need the midpoint. Which is just gonna be P0 plus the vector scaled by half. That's the midpoint. Okay. And then over here, we're taking like, I'm gonna call this P1 just to confuse. So this would be, so how do we calculate that? Is that like, the point of the branch subtracted by the start position. Oh, sorry, you don't see this. Yeah, so I calculated this midpoint like this. You take the start point, you add the, this is kind of the relative, the whole vector, or like, this is like the end point minus the start point. And then you scale that by half to get the midpoint. And then you take the midpoint sorry, I need to think about this here. So you take the midpoint is over here. If you subtract this, we basically get, don't we get like, we go up here to get this? No, wait. Or do you take this and subtract that to go over here? Yeah, okay. So you go here, you subtract this to go here, and you get there. Okay. So you start, okay. So you take that, subtract the midpoint, this midpoint, which, and then you get over here. So start. So you don't start with this. You do the start position, subtract the mid position. There we go. Okay, that's P1. And now we take the dot product. I mean, I would take, I don't know, this makes more sense in my mind to take this. Maybe it doesn't matter, but we take the normal now, because now P1 is like relative. It's a point. It's a point, start point relative to the plane, and we take this normal. So now they are now like aligned to work together. So now we can take the dot product. This is projected onto the normal. If it's positive, and we don't care about this distance. If it's positive, it's in front, negative, it's behind. So we also do P2. And dot product, the normal. Don't care about the distance. Like maybe there's some kind of weird optimization with the distance, but I don't know. This makes more sense to me. And yeah, I mean, it might still not work. No. Okay, I see something. I mean, there might be another bug somewhere. You see when I'm clicking, it updates. You see the red dot at the distance. Where is it? What the hell? Oh my god, okay. Okay. I want to do a thing. I want to visualize if our BSP map is actually correct. So let's do that. Let's go here and we'll go to the BSP. We'll I want to go through each segment. So these are the calculated segments. So they might be split and stuff as well. They should have a draw function, yeah. So if we draw all the segments, we should see them, yeah. Now you can see that it is kind of bugged a little bit. It looks like some segments don't actually exist. I'm not sure if that's actually the case, or if it just looks like that, but yeah. Okay, so that's the segment. Now we probably I wanna draw and I guess depending on the player position, wait. So what is A, if it's A in front of B? A is in front of B. So if, well, I guess it doesn't matter. So I want to draw like if A is in front of B, wait, what the hell does this even mean? We get two vectors. This is like the cross product thing. I don't understand this. Okay, it's the relative. And vector? Wait, this is... No, the vector, this is this supposed to be the normal? No, because we're taking like the cross product. So it's different. Okay. Thanks. Sorry about the noise. Sometimes my hands are does that. Wait, where were we? Over here? then this is the start position, and this is the vector. So apparently this also works. Okay, and then right, so depending on if it's on front or not, I would like to change maybe the color. If it is on front, I would say green, otherwise red or something. And now we need camera position. There we go. Okay, and there you go. Now we can see that, okay, those that are facing away, I guess, from us. Oh, wait, no, that's not. No, that is correct. It is correct, because we're technically in front of them. Yeah. So that seems to work. You can see they are green if we're in front, if we're facing them. Otherwise, they're red. So that seems to be correct. Okay. Now I want to see if this also works, like if my intuition of this is correct. So if we take, is there like a draw arrow or something? Probably not, no. I mean, we could do like a cone. I just want something to like point. So let's do so I would like to get the normal, and in my mind the normal is simply the vector rotated by -90 degrees, because it's rotated clockwise. Hopefully that's correct. That might be mirrored, so I might be rotating the wrong way, but let's see. So we do that, and now we want to, well, we have the center position, so we can get the normal. The start position of this arrow should be the center, and then the end is like center plus normal. So if we normalize and then we add, I don't know, maybe this is enough. So we normalize that, and now we want to draw a line, I guess, 3D. Start position is the center, end position is the normal plus the center. Color, let's use the same color. So this should technically just shoot straight out of, oh, wait. Normal start is vector 3 init, center x, 0 center y. normal normal 3D all right. What? Okay, this might explain a few things. And also this looks very strange because it's like we have two segments kind of sharing space. That should not happen. So that could be an explanation of some of the bugs we have. Yeah. Okay, but I think maybe it's not you know, angle. Maybe it's like radiance here. So it's like sometimes it's kind of strange because sometimes Rayleigh uses, you know, degrees, and sometimes it uses radians, and it's not clear when you should use one over the other. So this would be like pi over 2. Oh, 2.0. Okay, that looks more correct. Yeah. All right. Okay. I'm just gonna try this here. I want to have a little. I want to have a little arrow. No, wait, that's the start. Man, I wish there was a function that turned it into a 3D. What was that function called? Like a function where you could give like a string that would kind of shuffle, or not shuffle, but it would rearrange the dimensions based on the string. Maybe that was for 3D only. But this should be a rotate, yeah, rotate by axis. Which is the y-axis. Okay. Awesome. So I think we do times 3. Yeah. Now we got these little arrows. I just wanted to do that. Okay, anyway. Now. What the hell was I doing actually? Yeah, so we have these. So now we can see. Okay, so actually, one fix that we can do now is go to the BSP. Somewhere we have like negative 90 here. And they should actually not be negative 90, it should be negative pi times, no, over 2. Which is for 90 degrees in radians. And now, did it actually fix everything else? No, it didn't. And now this still doesn't work. Okay. Oh man. It's like if we're aiming this way, it's almost like saying we're always looking at something solid. If we're aiming this way, it's like not, it's like the other way around. But now I'm, okay, now I'm in another node, I think. Okay. Maybe we should fix the issue first with the BSP not being generated correctly. So if we go over here, we can see that, well, this one is very trivial, so it looks correct. But if we go over here, we have, you know, a huge chunk missing here. We have 2 segments on the same place, which shouldn't happen. They should never overlap. And same thing here. So there's some weird thing going on when we actually do the splitting calculations, which is over here. So let's see. Now this is also like, I'm not exactly sure exactly about all of this, but I guess it's this, the other segment position relative to the splitter. So it's gonna, it's, so what we're doing here, I think this is trying to calculate if we're on front or behind the splitter, if this segment, yeah. The question is this the splitter segment or the other segment? I guess this is the splitter here and this is not. And this just takes both vectors like this. I'm gonna double check if this is correct here. So let's go back to the video. And this is the intersection part. It's not building the tree. This seems like another kind of calculation here. Like here we're not using that weird cross product. Here we're using like a dot product. Because I think the BSP creation was from another video. This is the intersection part. Oh, what is this? Recursive hull check. Yeah, that's still the same. Okay, here is that video, I think.
A new class named Sector.
Level design with BSP. No, I think it was...
Is T, which is the ratio of these products. If we analyze... So we've got...
Split space.
the
Yeah,
splitter,
here we go.
put it in the node, and now we have to iterate over the remaining segments to determine what to do with those. Define a function in the utilities file. Values of the so-called numerator and denominator similar to what was shown on the slide.
Yeah, it's the splitter splitter vector. So that is the same as we have.
And the first thing we'll check is the collinearity check, but since the numerator and denominator values are float, instead of 0...
I just want to double check this again. I've double checked this like 100 times. But it's like we have A and B, 0 and 1, A and B, whatever. A plus AX times BY, AX times BY, minus BX times AY. Yeah, that is correct.
And having imported this function,
hello,
let's find the
robotic
values
head.
of the
Welcome,
so-called
welcome.
numerator and denominator similar to what was shown on the slide.
Oh, sorry.
And the first thing we'll check is the collinearity check. Let's...
Yeah, sorry, I saw you rated 5 minutes ago. Yeah, thank you. Oh, also Borchecker rated. No, wait, that was 4 days ago. So, I'm so bad at reading these things. But yeah, thank you.
Since the numerator and denominator values are
We
float,
are
instead of 0, we should compare their values to some
creating
minor epsilon value.
we're learning about this old optimizing algorithm called BSP, used in Doom and Quake, among others.
And collinearity in our case is when the splitter and the segment are on the same line, and then we always put each collinear segment in the list of front segments.
Yeah, and right now we're just double checking if something is wrong, because there are some bugs in our current implementation.
Now we consider the case when the splitter and the segment are not parallel, and if their ratio is between 0 and 1, we can find the splitter and the...
Wait. Cross to the segment start minus position. Okay. Yeah, so cross 2D. So this is the first thing here. That is the cross to the segment start. Is this? Yes. Minus the splitter position start. That is correct. And then the splitter segment vector, which is just the start, or I mean the end minus the start. So of the splitter. So that is correct. And then they take the denominator is the cross of the vector of the splitter and the vector of the segment. So that is correct as well. And then we have these ones, which are looks to be correct. And we haven't switched them around or anything like that.
Now we consider the case when the splitter and the segment are not parallel.
I mean, there might be the case that something is like wrong here in this algorithm. It's like an AI voice and everything, so I'm not sure. I'm just trying to see if They got the source code as well. 2 line segments intersection. Okay.
And if their ratio is between 0 and 1, we can find their intersection point. In this case, our initial segment is split into 2 new segments.
Yeah, numerator over the denominator. So if the denominator is not 0, which is what they also say here, we get this calculation here, which is numerator over denominator. And these are floating things. If the intersection is between 0 and 1, we take, whoops, intersection point is the start of the segment plus the intersection scaled with the vector. Yeah.
And since the segment class will have many more attributes, we can import the copy function for convenience. So we have 2 new segments, and let's label them as left and right, and we create them as copies from the original segment, while only reassigning.
Okay, let's look at the next part here. So we have 2 different segments, because this is where things might go wrong here, because I can show you here. Like this is kind of what we have here, and you can see that this wall is like one. It's like one segment, or yeah, thing here, and then we got this thing, which is split from possibly some wall from over here. It looks kind of weird because it's split here, but then we got these overlapping segments. So this every arrow is one segment that points like outwards, if like it points in the direction that the wall is facing. And we've got here, it looks like kind of correct because it's like they are not overlapping or anything. Well, actually they might be overlapping, I'm not sure. It doesn't look like it, but here definitely overlap, because otherwise there would be like an arrow over here probably. They are overlapping these segments, so we're getting these double segments, and we also don't cover the entire thing. So I don't think we shouldn't ever get these double segments like overlapping. I don't think that shouldn't actually happen. So there might be something wrong here. So what's happening is that if another like plane in the BSP is dividing a wall in 2, or it intersects the walls at some point, we have to split the wall up in 2 to keep the 2 sides apart. And one of the segments would be in front and the other would be in behind. So, and these are the 2 segments here. And so the first one starts at the segment starting point, and we end at the intersection point. The intersection point is calculated here. And yeah, and then we get the other segment is starts at the intersection point and ends at the end position. So that seems correct for now. And then we keep track of the original wall that we came from here. We have the numerator is more than 0. Then we flip them around. That basically means if they should be like in front or in the back of the thing. But that shouldn't affect their like position and everything. So I'm not actually sure why that would happen. If we don't have an intersection, this continues down here, and then we put the whole thing in even. We don't do a split. So it's only when we're doing splits that things go wrong. So it should be in here where things is going wrong. Where things are going wrong. And I did this kind of weird thing where I put this into a tuple so that I can just, when we do a swap here, we just have one swap thing. But maybe this doesn't work. I don't know. Maybe we'll do like, we'll try this. R segment. I'll keep this, hang on. I'll keep this this thing around, and we'll copy this over, and we'll do R segment is this, and left segment is that, and then this is going to be segment wall, model ID. Okay, and then we have like if the numerator is more than 0, then we flip the thing. So now we flip. But the thing is, like, if we just say that our segment is left segment, now left segment has been overwritten. So we need like a temporary segment that we copy. Is the left, and now we can overwrite. Now we can do this as well. Wait, no, the R segment, we need this. The R segment is overwritten, so there we go. And then we do, whoops, we do these two. This is the R segment and this is the left segment. So I don't think this will do anything, but I mean we can try. Oh, sorry, this is the temporary segment. There we go. It would be kind of strange if this actually solved the issue. Okay. I mean, okay, yeah, it does actually seem to solve this issue. Okay. I was actually not expecting that, because that seems like some kind of bug in Zig or my misunderstanding on how it should work. But yeah, that looks way better now. Okay. So, lesson learned. You cannot create a tuple and then swap the contents while assigning the same tuple with like this. Okay. I was trying to be cute there, but yeah, that didn't work. Okay. Cool. But that was yeah, that I mean, good that it was solved, but I'm surprised that it actually worked like that. But okay. The more you know. So there you go. But the problem still remains now. So okay, so we solved that issue. Another issue that we're trying to solve is that we're using this BSP structure to find intersections when you do a rake cast. So if I click my mouse button, it should shoot, and there's gonna be a red dot somewhere. And of course it doesn't work because that's the bug. So there you go. There you can see the dot at the distance there. So it seems to actually get stuck on a line here. it seems to get stuck on like the main divider line, like the root node. I wish I could. Maybe we could like write out the number or something of each device, like each splitter. And also, if I'm over at this side for some reason, I'm backing out. So I'm clicking. I'm standing over here. Then it like gets stuck on this line. If I move over here, click, I'm back. It gets like, you know, it's stuck on wherever my current position is, because if we're standing in what the game is thinking is like a solid block, it just stops at the start position of the cast. So that's why this is happening here. But this one seems to be stuck on a line. So there seems to be either something wrong with what we're considering to be like a leaf or something. And this should definitely not be a solid over here. Like everything, like these, the things inside, now are inside like a solid block. So this should be a solid, while this outside here is not a solid. So there is something strange going on there. So let's go to collision. And we'll look at what is happening here. So we're taking two 3D coordinates, we're making them into 2D coordinates while throwing away the Y position, which is just, you know, up and down. And then we're trying to figure out the intersection point with a recursive algorithm. And then when we got it, we got it. If we don't get it, we get a null, so there's no intersection point. Otherwise, we get an intersection point, and then we're creating a new point, and we're using the Y position of the starting position. That's not like ultimately correct, but I'm just doing it to have something there. And how does this algorithm work? Well, it's kind of hard to explain if we're not using like the diagram. But maybe we should go through it one more time so that we can get a refresher here. I'm not sure how much time I have now actually, so I'll try to make this quick here. Okay, I have this demonstration here. So basically, if we start to see okay. Let's remove all this thing. So this is the level here, right? So the BSP is constructed by, I'm just showing the half of the level here, but it's constructed by dividing the space using these line segments. So that's how I'm doing it anyway. So basically we just start with, so the level is like this looks like a Doom level. Like if you ever used a Doom level editor, it kind of looks like this. You have a top-down view of a 2D kind of map with these lines everywhere. So these lines represent walls. They could be solid walls. They could be walk-through, just lines that are marking an area. But in this case, I'm only working with like solid walls in my current demo thing. So these are all solid walls. And the arrow represents like the direction of the wall. So if you're over here, you're in front of the wall. If you're over here, you're like this wall here. You're over here, you're in front of this wall. If you're over here, you're on the back of the wall, like behind the wall. Okay. And how it works is that the algorithm picks one of these walls. So the whole level consists of these segments. So we have like 8 segments, 1, 2, 3, 4, 5, 6, 7, 8. Each segment has a start position and an end position, and also like a direction. So we start by just picking one by random, one of these segments. Let's pick this one. And so we create this line which splits the entire space in two. So you have and we also keep the direction of the thing. So this is in front. This now whole space has been divided in two. So this space now is in front and this space is in back. Okay? So that is how it works. You have in front and then the back. So that is the binary part. We're splitting in two. The world is split in two. And now these are totally separate kind of spaces that we can continue recursively with this algorithm. So next up, we're doing the backside first. So we're taking all the segments that are behind, and we are doing the same algorithm on them. Now I'm skipping a few steps because I'm taking this is a trivial example because I'm just showing how it works generally, but there are some other steps. If this plane was to hit a wall, you have to split the wall in two in order to keep things behind or in front of each node. Okay, but let's just continue here. So next up, we split this one. So now we have another node which is behind here. So this node is split in two as well. So it splits this world, you can say, this sub-world in two, where this is in front and this is in back. Okay, and then we continue doing the same thing, and there we go. And now, in the last part here, we end up with two kind of empty spaces. You have this space and this space. However, this space is behind. So what I'm doing is I'm automatically assigning this thing that is behind, I'm assigning this to be a solid. So this is a solid space, which means that you can't pass through it. It's a solid block of space. Okay. And then what we do is, how do we use this? Is that we have a player here, and if the player wants to move over here, let's say, or shoot over here, what we do is we cast array. So we have a starting position, which is the player start, and then the end position, which is over here. If you're shooting something, you probably have longer range than that, but I'm just doing this to demonstrate. Let's say you have a short range weapon or something here. So we start over here. Now we can determine from this position. So how do you use the BSP tree? Well, this is the root node over here. This is the root segment, and we can determine, are we in front or are we behind this node? In that case, if let's say you had an arrow, or let's say you had a ray that is going, I need a new layer here. Let's say you had a ray that starts here and ends over here. Well, both of the start point and the end point is in front of this node. So that means that we can ignore this one. This isn't part of, let you imagine that this isn't part of the level. But we're both in front of this node, so that means we're entirely within this the front side of the node, which means that we can check for intersections in the front side, or if the front is an empty space, that means we don't intersect anything because there's nothing there. If it's a solid, that means we are colliding with something. So then we pick the start position as the intersection point. Yeah, I feel like I need more diagrams to explain this fully here, but we watched a video before as well that showed this, but I'm just going through it to kind of also repeat a little bit. But let's say, so this one is in front of this node and this one is behind. So that means that we now need to split this line in two. So we split the line, the first part, let's pick like a green color or something. The first part, whoops, that was not great. Maybe this. Okay. So we split this in two rays. So this is one ray. It's kind of hard to see because of the low resolution, but imagine this part here. This is one ray, and then the yellow is the other ray. So we split the ray in two, and then we do the same algorithm, except now this is the ray that we're measuring with the front of this, and the front is empty at this point. So this doesn't actually that results in no collision for these ones. So then we continue with this ray, which we continue the algorithm on the back side of this node, and the back side is like over here. This was the node that we created. This was the back child, and well, both of these points are behind this wall, so we should continue with the behind node. I think the behind node is like this one, and then still both nodes, both points are behind this wall, so we continue with this node now. And now this point is in front and this point is behind. So again we split it in two. So we split that in two. Now this ray is compared to this node, which is, of course, it's inside this node and it's an empty node, so there's no collision there. And then we have another ray, which is this last one here, which we compare. The start position is over here of this ray, and the end is over here. Both are inside of this. This is a solid, so we're picking the starting point of this ray, which is this point over here. So this is the intersection point. Well, it's probably more likely over here. Whatever. It should be like on the actual line. So now we have found our intersection point because we're in the solid and we just pick the starting point of the ray. Because the whole level is divided into these spaces. So that way, I'm not sure if I made a lot of sense. I made sense to me internally at least. But now we've found our intersection point. And that should, I mean, yeah, this should represent the way that I'm trying to do this algorithm, like in the code as well. So really, whoops, if we go back to the code, and that's what we're doing here. So we get the start and end position. Now these are always going to be in the actual, inside the node, and this is the node that we're comparing to. So the start and end positions are always within the node itself. So they are entirely within the node space. So, and then we check like, okay, well, is the node empty? Like it doesn't have any children and it's empty. Then we don't actually have an intersection, so we return null. If the node is solid, we have an intersection. That's just the starting point. So that's just returned straight away. Otherwise, we need to do the whole checking if the points are behind or are they in front and so on. So here we do some calculations that is trying to calculate if we are in front or in back. So we have our position, you know, starting position, end position. We do a dot product calculation to see, are we like in front or behind a wall or a split. All right, yeah, you do that, Robotic. Thanks for the raid. See ya. So T1 will represent, like, if T1 is positive, we're in the starting point is in front of the wall. If it's negative, it's behind. And for T2, the same thing. So if T2 is positive, then the end point is in front. If it's negative, the end point is behind. That's the idea anyway. And then And then we check, like, if both points are in front, then we simply pass them along to check against the front node. If both are behind, then we do the same thing, except we use the back node. Otherwise, that means that the start and end are like indifferent. They are in different nodes. So one is behind, one is behind and one is in front. So we need to calculate a couple of things. We need to split this ray up in 2 rays now. So we need to calculate where we should split the array up, and that is this this mid point here, which is the start position of the ray, and then we add a difference, which is just the relative kind of vector of the ray, and we scale it by the ratio. So we calculate the ratio here. And I'm actually, you know what? This ratio is probably wrong now, because we kind of changed how this works here, this calculation before. So I think we need to rethink about this ratio, maybe. But anyway, we calculate the midpoint, and that's where we should split the ray. And so we have 2 rays now. So we check the intersection of the first ray, which is start position, and to the midpoint. And we check whatever side is like, if the start point is like in front, we should check, we should use the front side. If the start point is behind, we're using the back side. Same for the end point there. I really want to do this because it just feels better here to do it like this. Okay, and then if the start point, if the first like part of the ray, this is like the last detail here. If the first part of the ray, of the split up ray, which is, it's that's what we should check first. If that intersects, then that should be the result. If it doesn't intersect, we should continue with the second part of the ray. So that is how that works. All clear? Yeah, but something does not add up here, as it seems. Now let's think about this ratio here, because before I was kind of following like a guide on this, and they used some other type of calculation, and so this might not be correct anymore. I changed this around, but I never changed the ratio around. So let's think about this. It might still be correct, but it also might not be correct. So it's like T1 is representing if the start position is in front or behind, and also like how far. And so we take the difference, we take this and divide it by the difference. I'm trying to picture this in my head. So it's like, okay. So it's like if we have this little mini universe over here, we have a midpoint Whoops. Okay. And we have what do we have? We have this normal that goes out like this. Let's use this color. So we have a normal that goes out like that. And then we have the ray, but it's like we have two positions. So basically we have one which goes out kind of like this. I'm not gonna draw the arrow, but because it's like implied, we're always starting from the origin. And then we have the other one which goes kind of up like this. So here's the starting point and here's the end point of the ray. Now you can clearly see the dot product of this goes up here, and then you take like the length, because we're taking the dot product of this onto the normal. So that would be like the length of that, which would be like, I don't know, a couple of like 4, let's say, positive. It's some kind of small positive number. So T1, oh my god, T1 is equal to some kind of small positive number, let's say 2. Okay, and then T2, whoops. I was trying to do like a fancy paste because the new GIMP like always creates like a new layer, and I'm still trying to get used to it. Okay, so T2 paste, where is that? Paste in place? No, I don't know. T2 equals, so T2 is this one, which is projected down here. So it's like negative, I don't know, let's say it's negative a little bit more. It's like -3. Okay. Whatever. Okay, so the calculation is taking T1 divided by T2 actually, yeah, no, it's not T2, it's T1. Oops. Yeah, T1 minus T2. Whoops. Wait, what? Oh. which is oh my god, let me merge this. Maybe I should have used another program for this, or I don't know. Okay, so what is this? This is 2 over 2 minus 3 equals 2 over negative 1, which is equal to negative 2. And that is not a ratio. What the hell? That is not a ratio. A ratio, or it's a ratio, but it's not a percentage. Like it's not between. It should be between 0 and 1. Is the 2 should be over here? Maybe, but what if T1 is larger? So if the T2 was over here, this would be positive instead. So that would be 2. So that doesn't even work. I don't understand this calculation. Am I doing something wrong? Maybe it is correct, but we need to figure out a way to get the midpoint. We need to figure out this thing. Yeah, okay, so T1 is like the distance on this line, and T2 is the distance on this line. So we would need to get like where they meet. No, we need to get this point. Like you go up there and you go down there. We want to find this point. So we got kind of what we have is like now we have the correct ratioed numbers, where this is actually, no, this is negative. T2 is negative. I forgot. T2 is negative. So actually T2 is negative 3, so it should be plus 3 here. So 1 plus 3 is 4. Like how I solved that. Okay, and then what the hell? And then this would be 2/4, 1/2. But that doesn't make sense though. We should not be 1/2. Wait, did I do this wrong? 2? No, 2 plus. No, wait. It's 2 here. 2 plus 3 is 5, which is 2/5. Okay, and that doesn't divide really. So 2/5 from the start over there. Yeah, that makes sense. Okay. So it does make sense. Okay. Okay. What is then wrong? Maybe we should visualize this whole thing, actually. We should actually... Whoops. Okay, so what I want to do is I want to create a struct, which is like an intersection information. I want to keep track of all the splits we're doing with arrays, all of their start and ending positions, and I guess we kind of could keep track of like the order, maybe, I don't know. Let's just have a list of arrays where array is just a start point and an end point. Okay. And then over here. Actually, actually, you know what? Let's make this into an array list. Of arrays. And what we'll do is we'll keep track, we'll have this intersection info over here as a thing that we're keeping around to edit as like a context. Okay. And now and then that is, you know, it's kind of returned, I guess. It could be something that you pass along here, and that we also give. Okay. So whenever we return here, we should return like this is like the end, this is like the terminating pieces here. So we should actually, every time we get here, either one of these, we should append array Okay, you know what? Let's make this managed, actually. Wait. Is this gonna get deprecated? Well, it is deprecated. Well, it doesn't matter. Okay, so append start position and position, and well, I guess this would be an error union now as well. Okay. Same thing over here. Both leaves, leaf branches. We just append the array. So now we can get the positions of where all the rays are split up. Because if we don't get over here, what we're returning is just another call into here. So as long as we just do the terminators, that should be good. Okay. Right. So now over here, what we can do is we can say, along with a hit queue, we have intersection info. Which is, well, I mean, we could just initialize this. That's fine. All right. And if we get a thing here, well, actually, every time we shoot, we want to clear this. I'm just gonna say clear here. We want to clear it. Now, actually, let's just clear this. We're probably not going to use this for anything else. We're going to clear retaining capacity. And then we're going to give the intersection info here. So it's going to populate that. And of course now we need to try this one. All right. And that's it, I think. And once we've done that, we can draw the cube. So here's like we're drawing the hit cube. We also want to draw now the intersection points. So intersection info, or the rays, I mean. So we're going through all the rays. And we're gonna get start position and the end position with a destructuring thing. Okay, so now we can draw that. We can also make it into 3D. So let's do like 3D. X, 0, and Y. Okay. And I will do draw line 3D, start, and let's just do red. And of course, we don't really see the start and end. Like if the line starts when another line ends, it's just gonna look like a continuous line. But let's see if this works first of all. Okay. So it looks like it actually does work, and it goes quite far there. I was actually expecting this not to work. But okay, so but that's good, we can rule some things out. But what I want to do is add points, like little dots, to where they are actually split as well. So we don't know how many splits we got now. So let's add a bunch of cubes now as well. So we will do draw cube. Sure, let's make them solid. So you need a position, width, height, length, and color. Okay, so let's make the color like red as well, or maybe, I don't know, blue, or no, yellow, and or orange. It doesn't matter that much. I just don't want it to look like the background so we can see it. Position will be start position 3D, and the size I'm just gonna say 1 for these ones. Okay, and then here's the end position as well. So there we go. Now we have the start and end. Maybe we should also, okay, so start is, let's say the start is yellow and the end is orange, so we can see the difference there. I mean, they should overlap, I guess. Huh. Can we actually get to the end? The end is quite far. Yeah, we can see the end. I saw the little thing there. Okay. So interesting. I mean, I would expect here, for example, there to be a split here, but there's not. So there's something wrong, obviously, with this algorithm here. You can see, obviously, there's a split over here. And interestingly, it actually goes further. I would assume it would skip past. If we actually get an intersection, it shouldn't continue, actually. But yeah, there are a couple of issues here, so because if it gets a result, we should return that and then abort and not check the other split. So that is strange. Actually. You know what? Let's do this. Let's draw them, but not exactly at the start and end position. Let's actually move them along the line a little bit so that the start position of one does not coincide exactly with the end position of the other. So let's add a little bit of difference or some kind of small number to the thing. So I'm gonna add n, and here I'm gonna subtract n. And what is n? N is going to be end position minus the start position, and then we normalize, and I guess that could be it actually, because it's gonna have 1 as a distance. Maybe we can even scale it down to half. So then kind of the lines should meet. Okay. Interesting. Yeah, here's the setup that we had. So start, yeah. And there you can see it's kind of lining up here. So end. I just think I didn't take the rotation into account, but yeah. So there's the end, and there's a start of the next one. So why doesn't it abort there? I would assume it should abort. So that is one issue. The other issue is, of course, why does it intersect here? And same thing over here. It's like we have like, I mean, it kind of looks like we do get some of the splits considered correctly, but why not all of them? I mean, it could be that the BSP is not correctly calculated, because we can't we don't visualize the relationship between the nodes. We only visualize each node's front and back and area, sort of, or the plane. So we don't know if the relationship is correct. Like here, yeah, here we are like, yeah, in front or behind. We also have the is on front function, which we did flip to make something work, but let's flip it back and see what happens. Yeah, see, it's kind of weird now that it's like the other way around. Yeah, it didn't fix the issue here, but it did do something, I guess. It's times like this when you're just like, there's so much going wrong that you feel like giving up. But yeah, okay, so a couple of things. You see some walls are green and red. They switch color, and they are supposed to switch color depending on if we are in front of it or not. While red means we should be behind, and green means we are in front. So that's why I flipped the sign, because it seems to be the other way around, but maybe only for some of these calculations, like, I don't know, or maybe I should flip the thing that I'm trying to check. Like maybe it's not A is in front of B, maybe it's B is in front of A. I don't really know. Where was the thing? Segment. Oh yeah. So maybe this should be the other way around. But it wasn't in the other calculation though. If we go to the video, there should be the function. Yeah, here.
Find functions that represent the same cross product, but taking into account its sign. So, we will traverse the tree recursively and taking into account which side of the splitter the camera is on. So we build a vector to the camera and use cross product. That is our function that takes into account the side.
So here's splitter start, splitter end. We have the relative position of the camera to the start of the splitter. And then we take this, we calculate this is on front depending on that. To get if we're on front or not. But again, I guess it also relies on if the X and Y is like correctly flipped or whatever. Because it seemed like one of those were kind of weirdly flipped for us. But yeah, apparently this should be the first one and this the second one. Yeah. Position 0 is the start. P is the position we're looking from. And then we're using the vector. And not anything else. Yeah. And the vector is just end minus start. So it's like the relative vector of the thing, of the line. I mean, if we do this, it should be the other way around, right? Yeah. But it just feels weird. Like, why would it be flipped? I don't know. Maybe it's an error in the video. I need to analyze this cross thing here because I don't actually understand this. I mean, it's similar to the dot product where we're trying to figure out if we're in front or behind something. But it seems like the cross product needs, or it works with like less information, or I don't know. It feels like we only, what you need is like the start position of I don't know, man. I actually don't understand this at all. But yeah. Wait, was it this way or the other way? Okay, well now it seems better. And it's like if we are on front, we are green, otherwise we're on red. So yeah. Okay, let's do this. Let's simplify the map a little bit. Let's do like 2 cubes and let's reduce the size. Now the map is always the same because we always give the same okay, maybe we should use a different seed. We'll try seed 1. I just don't want the cubes to intersect. I mean, okay, maybe we need a larger area. 30 by 30 maybe. Okay, perfect. See here, now it's very clear. It's like we have a root node, which is either, it's kind of unclear which one is the root node, but it could be this one or it could be this one. It doesn't really, yeah, because it's not this wall, because this wall is split. So you can see that from this wall, it's splitting this wall in 2 segments. And this wall is also split by this wall. So it's like this wall has a node which splits the whole world in 2, as all the other things. And then this is split up because we need to keep track of which is in front of this wall or in back. So this segment is in front and the other one is in back. Same thing on this side. This is behind that wall, this is in front of that wall. And whoa. Yeah. I mean, I guess this makes sense, except for the intersection point. The intersection point does not make sense. But it makes sense that we would actually split here, because we have a segment over here. So it does make sense to split here, but it does not make sense to have the intersection point be there. Is it just because we're behind, or I don't understand. There's something missing here. Because we should start at like the root node. I'm pretty sure. Or do we actually? You know what? Maybe we don't start at the root node. No, actually, we start at the node that is closest to the player. That's right. We start. So what we should start at is like the area where the player is in. Whoop. So how we find out the starting thing is we're taking the first node in the traversed thing, but that doesn't necessarily be correct. Shouldn't we always start in the root node? I don't know. Let's actually just do. Let's just take the root node. I was gonna say that looks better, but no. It's like okay, but if we're over here, then no. Now it's always colliding at the start point, and it just stops. It's like the solidness is wrong. Yeah, it always stops behind. Or I mean, yeah, it always stops. You can clearly see the line is going here. This is the root line. That's the root line, and we stop at it. Yeah, that is just wrong. What the hell? We should get at least one subdivision. You know what? Let's also print the tree. We had a print tree thing. Yeah, we are printing the tree. So let's look at that. So here's the tree printed out. It's maybe a bit hard to see, but maybe I should use no, let's whatever, let's just look at this one. Okay, so we've got, here's the root node is a branch, which is this here. Front is a branch. Front branch, front branch, front branch, front branch, front branch. Front empty, back solid. Back is a branch. Doop-a-doop-a-doop-a-doo. Yeah, I mean, it looks correct at first glance. Wait, is it flipped? Look at this. The front should have both should have children actually. Something is very strange. Let's do this. Let's see. So, do you have an ID? No. Well, if you're a branch, you have a segment ID? So we could see if the segment has the same ID as the root. We could draw it differently in a different color. So we have this segment. I mean, I guess the ID would be like 0. It has to be a branch if it's a segment, I think. If this is 0, it means it's the root. If we are root, I'm gonna do purple. No? Is it not populated, or am I not understanding this correctly? We are setting the node of the segment, but the question is this segment correctly modified? Because it might be like copied and stuff. That's the problem, because we had an issue before where the segment ID was not actually up. It was not properly updated. So it's like if we add an ID here and we set you to branch segment ID. No, because this is a different segment, right? But then we can say segments items branch segment ID dot ID equals branch segment ID as well. I think that might work. But that still doesn't work, okay. Yeah, okay, so the node might not work, but now we have the ID anyway, so we can say, so we don't need to check the branch, we could, or the node here, we could just check dot ID. Okay, now we should see the purple. So this is the root node, and that is where, so my assumption there was correct. Okay, so it's like it stops at the root. Why is that going through a little bit? Oh, I see. It depends on the angle. Okay. So that is the strange thing, because the root should have both back and front children. So let's actually check this. So root front. You have to be, you are a branch. And then the back. And root front is a branch, root back is also a branch. Okay, so they were both branches. But why are we stopping then? I don't understand. Okay. I think the mid position, I mean, yeah, it feels correct. If start side, if the start point is in front, we should use the front, otherwise the back. Yeah. And are we using like the correct nodes and everything? Should be BSP root, yeah. I am a little bit stumped. Thought I was gonna get more information out, like if I had more debug information to figure it out, but so far it all checks out. I mean, it's the ray intersection part that seems to be the only thing that's wrong at this point, from what I can tell. Because I was thinking, like, if the tree relationships was wrong, then that could have explained the thing. But really, now I don't actually understand how this is happening. Because the idea is that the ray starts here. Well, it doesn't end over there. We are seeing only the first part. So I just need to grab a glass of water. I'll be right back. So when we cast a ray here, we're actually casting it all the way over out there, like way over there. And then the things we are seeing here, well, it should be split up into multiple parts. And so we should be seeing another part over here, but then aborted at the start because this is like a solid area. And then it should stop over here. But we're only seeing this part, and we're seeing that the intersection point is actually over here, which means that it thinks that this is a solid area, and so it stops right at this start position. So yeah, so I like, it has to be something that has been wrong all along, and I've just missed it over and over. So, okay, again, the idea here is that we have a start and end position. The idea is that the start and end position is fully within this node. And since we're starting at the root node, the start and end position is like fully within this node's kind of world space. Which should be correct because we're talking about the root node. So the root node encompasses the whole world. So these two are guaranteed to be within that node. And then we divide them, if they need to, into like in front or behind the node's splitting plane. Which we are calculating over here, and we're doing the things over here. So here we're calculating if each point is like behind or in front of the plane. And couldn't we just use the is in front, is on front? No, because that is, we need an actual value. That's right. But here we could also use the cross that we used before, I think. I don't know. Anyway, this is supposed to give us the calculation needed to understand if we're in front or behind the splitter, as well as how far, because we need to know where to find the midpoint, which seems correct. Where the midpoint seems to be correctly calculated. But then now the problem is that, well, if both points are on the same side, which we're calculating here, then we just return a recursive intersection check for either the front child or the back child. If they are on the different sides, which should be happening in this case, we go down here, we calculate the midpoint, which looks correct. We calculate the sides. So we're calculating like if the, so the idea is that we check first, we split the array up in two, where they correspond to the front or back side of the splitter. So this should be, this is the front side, or I mean, technically it depends here, but in our case it should be the front side because the start position is in front. So it should be picking the front side, and then we stop at the midpoint. So these 2 points are supposed to be within the region of the front, and they are. And if this collides, we should get a result and return the result. Otherwise, we check the far side of the array, which starts at the midpoint and ends at the end position, and then we're looking at the back side in this specific case. And then at some point we get to these leaves here, which say that, okay, well, if we're in front, or I mean, if we have a leaf and the leaf node is defined as being empty, then we don't have an intersection, so we return null. If the leaf is considered solid, we do have an intersection, so we return the start position of whatever ray that we started with. If it's like this end point, this split ray, it should start at the midpoints, and that is like the intersection point of one of the planes. So, but that's not what we're getting. We're getting the start position of the camera, which is clearly, you know, in an empty region of space. So something is wrong. Maybe I want to have different rays depending on if they are what is it? If they are colliding or not. So let's add a color to denote. Or I mean, well, we could add a color, or we could. No, let's just add a color or whatever to denote if they are colliding or not. I was thinking it like an enum that would explain the type of ray instead. So there's the ray color, which should be this part here. And this one, the empty one, let's just do gray, and this one was red, I believe. Yeah, so you can see that it's always red. It always collides, it's always red. So something is going wrong, obviously. I just don't understand what. We could also go here to say... No, I think we know that we are going in here because we get the midpoint. Otherwise, we would see a ray that continues on. And we don't ever go in here. So the thing is though, you know what? This is the root node. How do we know that the thing behind here is solid if we start at this node? That is the question. Like if we go to the drawing again, and instead of checking there, we want to check this instead. That should always that should also be an intersection here. But how would we know that? What the hell is happened here? Okay, there we go. Because when we go over this line, we go to the back side, we go to this and check. And we go to the back side of this and check here. We go to the back side of this and check this one. And then we go to the back side of this, and that is solid. Okay. Yeah, okay, I guess that works, actually. It has to go through, like, the half of the thing, but it does actually work. And this one would like see that, okay, well, we got the front and it doesn't have, it's empty, so that should be false. Yeah. What is wrong? Man, I've been going through this like a million times now. Maybe we could find some more like information to add that we can see what is happening. I think what's happening, we're going in here because we never get over here. We're going in here and it's at some point something is telling us that we're in a solid. Like it doesn't matter if we're in a solid space or outside, it always says that it's solid. So we're going here, we're splitting it up. The back side no, and we're checking the front side first. The front side has children, it has these children, you, and you. Not sure which order they are considered, but we should be on like the same side of either of them. Not here though, but here. Like it doesn't seem to matter. But if there, we are on the same side of either of them, except for this guy, I guess. Oh. Okay, we got a different. Actually, we got a different. No, wait. No, it's the same. Yeah, it's the same. It's just that we got past this here. But yeah, my point was to say that now it's like we're on the same side of like all of these. So what's gonna happen is that we're checking, we're both in front of that, we're both in front of these, we're both in behind this one, we're both. Oh wait, we're both behind this one. And behind this one is a node that might be solid then. If this is the last node. Actually, it doesn't matter. Every one of these are like the last leaf. Wait. Okay, what if we had a line that went like this? So we're starting here and then we're doing this. Both of them are in front of this, so that should just be like an empty leaf. Yeah. And what if we're doing this? This is in front, this is behind. So we're creating two lines now. So this is in front. Yeah, both should be in front. Or I mean, yeah, now we're checking this child here, which is empty. So this one is like, it disappears. Okay, and then we're left with this one. Which the starting point over here, the end point over here. Which node are we looking at? We're looking at this node. So we're in front of this node. So we should just look at the front node. And the front node is empty. So this is also results in nothing. I'm just letting it cook a little bit in my brain. Slowly turning the whatever it's called, ladle in the stew. And perhaps it will get less cloudy. Like, I'm thinking like the most likely culprit is something to do with like the front and back calculations. And like, is the back side of the node actually the back side, or is it the front side? Like, because on the drawing, like if it's the other way around, then that would mean that well, actually it should get flipped though, because it should get flipped if we're inside. If we're inside a solid area, if this was actually represented correctly, like if this was like the other way around, we should get some kind of difference here. But there's no difference. Like the behavior is exactly the same, it's just that we're standing on the other side. It's like there's no difference between in here or here. Which is very confusing. It just feels like there's some miscalculation somewhere that I'm just missing. But I've been going through this I don't know how many times now. front segments go into front, back segments go into the back. Front and back. We return them first the front, then the back. We get first the front, then the back. And these are like new arrays that we create. Is it something to do with this? Because then I will lose my mind. We're creating new arrays. And we're returning the contents while also kind of releasing them here. And then we get them here, and we use them. This isn't used. I'm gonna remove this one. This should be correct. Okay. And here we're dividing all the rest of the segments to back and to the front. I mean, this might be the other way around here. Front segments, back segments. This might be like that they should be the other way around. I don't think so, but maybe. Wait. No. Nope. There's not a difference at all. There's no difference. Oh my god. What the hell? Hang on. An important distinction here, though, is that these segments should, I mean, they have to have the same rotational in direction here as they should have the same like direction. Yeah, so this should start at the start point and end at the midpoint and then end at, yeah, so that is correct. They should not be flipped because that will cause some mayhem here. This will cause mayhem, I'm pretty sure. More mayhem than we already have. Okay, it doesn't, yeah, you can see it kind of looks very strange now. So this is correct, yeah. But damn it. Is it the numerator here or what the hell? Numerators more than 0, then we flip them. Because I was thinking if these were like the other way around. If numerator is less than 0, numerator is 0 and denominator is more than 0, then it's a front thing. Otherwise numerator is more than 0 or numerator is 0 and the denominator is less than 0 or is less than 0, then we add it to the backside. Yeah. And here is the the kind of guide algorithm that we've been following. So I think I understand how it should work. It's just a problem of actually making it work. This isn't even the whole thing. It goes on. Yeah, so this part, here's the first part where if we're terminating, if we're solid, we have a collision from the start point to, wait, yeah, the start point, that we set the intersection to be the start point. And we have a collision. Otherwise, if it's empty, we don't have a collision at all. So that is also what we're doing, because we're returning null, which signifies that we don't have a collision. Otherwise, we do some calculations to understand if we are behind or in front of the segment line divider splitter thing, and if we are on the one side or the other side, we use the respective node to check recursively against that. If we are on different sides, we calculate the midpoint and split the ray up in two, and then we start to recursively check the first ray against the back or the first node, depending on which side it's on. And if that results in a collision, we're gonna use that point that we get from that. Otherwise, we're checking the other part, but we never get there because then we would see that being rendered. Okay, let's do this. Let us change the array. Instead of having color, we're gonna say array type and depth. I mean, let's just make this into a struct. Start and array type depth. So depth would represent how many kind of array splits have we done, I think. And then type is like, was it colliding on something? Was it not colliding on something? Array type is an enum. And I'm just gonna have the same thing here. Actually, it's just a leaf type of the BSP node. 1 second here. Alright, yeah, sorry about that. I actually need to go now. Man, I really want to just finish this at some point. So maybe we'll continue tomorrow. But yeah, we'll see. It depends on how much time I have with everything else going on. So, but yeah, that's gonna be it for this time. So thank you very much for joining me, and hope